So in today's video, we're going to take a look at L'Hopital's rule, but for some more kind of advanced and implicit cases, which require a little bit of algebraic manipulation before we can actually apply the rule. And so here I have two examples that I'm going to go through to kind of show you how you can approach these sorts of problems. So here we have the limit as x approaches infinity of x to the 1 over x. And if we're going to use direct substitution here in order to see if we can actually use L'Hopital's rule, we'll end up with essentially infinity to the 1 over infinity, which, I mean, I guess you could state that 1 over infinity would be 0, so you get infinity to the 0th power, which is a pretty strange kind of answer, right? Like would that technically be 1, but then it's infinity to the 0th power, so it's an indeterminate form, but it's not really one of the indeterminate forms that we need in order to use L'Hopital's rule. And so what we can instead do is we can just say that this limit is equal to some number L, right? We can just call our limit L. And what we can do is, because of the fact that the logarithmic function is a linear function, we can just go ahead and take, or not a linear function, it's a continuous function actually, I don't know where I got linear from. What we can do is we can apply the natural log to both sides of this equation, and you'll see why we'll do that in a moment. So this right over here tells us that the natural log of the limit as x approaches infinity of x to the 1 over x equals the natural log of L, right? And why are we doing this? Well, because of the fact that the logarithmic function is continuous for, x is greater than 0. And then what we can do is we can take this natural log and kind of move it into the limit. So we can swap the limit with the natural log, right? And so what we'll end up with is the limit as x approaches infinity of the natural log of x to the 1 over x is equal to the natural log of L. Is equal to the natural log of L. And now what we can do is we can just use our logarithmic properties. I mean, right over here, what we did didn't really change the value, right? We just swapped the limit with the, with the natural logarithm. That's, all right, because the natural log is continuous, again, for positive x values, or for x values greater than 0. And so what we can do now is we can use our log properties over here to simplify this expression, this kind of argument for the limit. And so this tells us that this will be the limit as x approaches infinity of, we can rewrite this as 1 over x times natural log of x, or we can just write it as natural log of x over x, and that's equal to the natural log of L. So here what we did is we changed the expression. Well, we didn't change it, but we just kind of restated the expression in a different way so that we can actually now see that when we use L'Hopital's rule, if we were to take the natural log of infinity over infinity, then this would give us an indeterminate form of infinity over infinity, right? And so now we can actually use L'Hopital's rule. Because initially we technically got an indeterminate form, but not one that is valid for L'Hopital's rule. But here, when we just use a bit of algebraic manipulation, we're able to determine that this will, that L'Hopital's rule is now, we can actually use it. It's valid in this case. And so let's go ahead and apply it. So we can take the derivative of the numerator. So the limit as x approaches infinity of the derivative of the numerator. The derivative of natural log is just going to be 1 over x. And then the derivative of the denominator, we know that the derivative of x is just 1. So it's going to be equal to the limit as x approaches infinity of just 1 over x, which we know that that's going to just be equal to 0, right? Because as x approaches infinity, the denominator gets infinitely large, the numerator stays constant. So here, this will be equal to 0. But now, we can't say that this limit over here, that 0 is equal to this limit, because right over here, what we did is we have the natural log, right? Because this is equal to the natural log of our limit. So the natural log of L. And so how do we undo the natural log? Well, we can just take e to both sides. So we end up with L equals e to the 0th, which is just 1. So that would be our limit right over there. And so that's how you can approach these types of problems. Just see how you can algebraically manipulate them using logarithms, and it will make your life significantly easier. And so you can use the same approach over here, and I'm going to leave this one up to you to try. But essentially, we can see that if we were to use direct substitution, even we're taking the case where x approaches 0, then we would end up with essentially 1 plus 0, which is 1, and then to the 1 divided by a sign of 0. Sign of 0 is 0, so this would just be 1 divided by 1 over 0, which of course is there's just many things wrong with that. And so essentially what you can do is you can again just set this equal to L, take the natural log of both sides and then swap the limit with the natural log. So the limit as x approaches 0 of the natural log of this argument over here, so 1 plus 2x to the 1 over sine x, and that's equal to the natural log of L. And then again, if you're going to work through all of this, then you should end up with a final answer of L equals, I believe it was e squared. And so, yeah, and I'm going to be honest, I took these examples from Khan Academy because I couldn't really think of any good ones myself. But essentially, this is how you would approach these types of advanced L'Hopital rule problems. It may not seem so obvious that you can use L'Hopital's rule at first, but if you just, use some manipulation using logarithms, which is something we're going to do a lot, especially in differential equations, then you can see how we can actually apply L'Hopital's rule and obtain the indeterminate forms that we're a little bit more familiar with.